Hello everyone, welcome back. In this video we'll be talking about face-centered cubic crystal structure, FCC. We're gonna have similar discussion, the arrangement of the atom, the relation between the lattice parameter and the radius, and the coordination number as well, all explained here. Now, the way that we call face-centered cube, it means that you have still, if you take a cube, by the way, we'll still stick with the cube, so I'm not gonna talk about the others, we always say cube. So if you take a cube, a unit cell that representing all the crystal structure, if you take one cube, there will be one atom at the corners. But at the same time there will be atom at the surface. If you will be able to, let's just show you this in a book. Yes, here it's much clear. If I zoom this one in here, you will understand. So okay, this is the corner. Look, this is for this guy here at the back, the corner. This is the center for this one, the corner. So you have one atom at the corner again, but we also have at the faces. Now when we say a cube, what do we have? We have face. I mean, those are the corner. We have 8 corners. And we have 6 faces. Yes, 1 at the top face, bottom, and then 2. We have 2, 4, 6 faces. We have it. At each face we have one atom. Don't know if you can. I mean, the easiest one is by looking at this one here. The easiest one, because in the 3D, the easiest one is by looking at this face. I mean, the other one are the same. So you can just look at this part here. It's easier to understand. We have one atom at the face. Now let's see that if I can show this one in a different. I wish that we are in a. He's better. I had this one in a 3D. I made them with some spheres basically. It's easy to understand. How those atoms are arranged. This is we call face. Look, this is easy to know that this is the face. Yes, this is the face here. It's at the face. So at the face, this is basically the face. And this is the face. We have 6. This is the face. And at the corner, we have one atom at the corner. And one at each face. Now when we say face, there is another unit cell beside here. Yes, beside here. So if I do this one, they will give me another unit cell here. This is another unit cell. So one at each corner, and look, this is the face. This will be the face at the bottom face, top face, and this is at that set. Now you realize that this atom here, will be shared between, the face atom will be shared between 2 unit cells. It's not as the corners. The corners are the same. Corners will be again shared between 8 unit cells. Doesn't matter which kind of crystal structure that you have it. It's in the cubic. The cubic crystal structure. The corner, so it is simple as the FCC or the other one we have it. The corner atom will be shared between 8 unit cells. However, the face atom will be shared between 2 unit cells. So that's why you can see it here. This is a half sphere. You can see this is a half sphere here. A half sphere at this face. There is a half sphere at this face, half sphere here, we have a half sphere as the bottom as well, half sphere as the other side. At each face we have half sphere. But still at the corner we still have 1 over 8. This is 1 over 8. Why? Because each corner atom will be shared between, divided or shared with 8 unit cells. However, the face atom will be shared between 2 unit cells, so we call this one half atom. It's going to be half atom here. However, this is 1 over 8 of the atom, yes? So we call them 1 over 8 atoms at the corners and half at each face. Now, why this is important to know? Because we will know how many atoms we have. I mean, if you add all of this part of atoms, I mean, if you add them all together, what will be the number of atoms within this FCC, the face-centered crystal structure? Now, face center, look, the face, basically the name comes by the face, because at each face you have an atom. At each face there is an atom. Remember, we have to slice them. Why? Because when we're calculating a unit cell, we need within the cube, not outside of the cube. So I've seen from the students they made this mistake. They say, sir, you said that there is an atom at the face of the crystal structure. Yes, that's why they call them face-centered cubic crystal structure. But for our calculation, we only take 1. So if I separate those 2 unit cell, this atom at the face will be divided into 2. We'll say, okay, half for this guy, half for the other guy. This is what we need to do. So if you calculate the atoms here, we have 8 corners, yes? We have 8 corners multiplied, each corner is 1 over 8, plus how many face we have it? Say we have 6 face. 6 face we have it in the cube. For example, this is 1 face, we call this one a face. There is a face, this is 1 face, bottom, the other side, the back, and this side. So total we have 6 faces, and each face we have half atom. So total number of atom here, that's gonna be 4 atoms. And this is the densely packed. I mean, the atoms cannot be denser than this manner. Now the arrangement, it's still in a cubic crystal system, in a cubic crystal structure. This is the highest number of atoms within a unit cell. You cannot put any other arrangement to make it denser. So 4 atoms in a crystal, in a unit cell. Remember, you're not gonna put those 4 beside each other. 1 at each corner and 1 at each face. That's how they arrange. 1 at each corner, you can see them here. 1 at each corner. There's the 8 corners that we have them. 8 corners. And then we have 1 at each face, which basically we have 6 faces. And we know that when we cutting them, slicing them, 1/8 of the corners will be for here, and those are face, half of them will be for the unit cell. The other half of this one for the unit cell. I wish that we were in a face to face. I could show it to you the way that those arrangement that we have it, the atoms, we will be able to slice it to see that, I mean, half of this one goes for the other unit cell. Now, what else we have to know on the face-centered cubic structure? We said that the relation between the lattice parameter and the radius. Now here we cannot say that A is equal to 2R. We cannot say A is equal to 2R. Why? because the, the corners are not touching. I mean, the corners here, look at this one. I mean, this is R, this is R, but they're not touching each other. There is a space between them. So I cannot say A is equal to 2R. We know that A is greater than 2R. A is greater than 2R, but it's not equal to 2R. It's not equal to 2R. So how do we find it? We find it in the manner that from the diagonal way, and the face diagonal, in the face diagonal, the atoms are touching each other. So the atoms are touching each other in a diagonal manner. You know, we need to know that how those atoms are touching each other. Why? Because from the center to the surface will be R, and from the touching point to the other center will be radius. That's what we need. In the face-centered cube, let's just show it to you in a 3D, which is here. Look at here. I mean, the way that the atoms are touching each other, it's in the diagonal. Look at this diagonal here. This atom touch this one, is touching the other one. But these two are not touching each other. Look at them, they're not touching each other. I mean, this one is not touching the one beside it. So on the edge, they're not touching. There's a gap between them. But on the diagonal, any diagonal if you take it, this is 3D, it's a bit hard to understand it here, but this is the easiest one that we can guess. Any diagonal you take it, the atoms are touching each other. For example, this diagonal, or this diagonal, any diagonal you take it, the atoms are touching on the diagonals. This is going to be useful for us to find the relation between the lattice parameter, which is A, and the radius of the spheres. So how do we find this relation between A and R? By using trigonometry. We know this is A. We know this is the lattice parameter A. Why? Because we have a cube. This is also A. Now, because we know on the diagonal they are touching each other, so we know that from this is the center, yes, center here, till the surface is R. This is R. This is R up to here, and from this one again till here, this is R, and the one in the middle, this is center is here, and there's going to be one R here and another R here. So the total diagonal length in a face-centered cubic crystal structure is equal to 4R. 1, 2, 3, 4 R's. Center to the surface, because they're touching, this is 2R, the diameter 2R, and there is another radius here, that became 4R. So if I take this triangle, the lattice parameter is A. Why? Because it's cube, this side is A, this side is A. We can find the relation between A and R. Why? Because we will write it in this manner, in the Pythagorean theorem, that we say that A square plus A square is equal to 4R squared. We know this one, 4R squared. Then this will be 2A squared is equal to 4R squared. You just rearrange them. You will end up having A equal to 2R root 2. There is another way to represent this one. Let's do it. So let me just, do we have it here somewhere to believe that we have it somewhere? Yes, it's here. We have it. I'm going to explain over here. It's fast basically, but I'm going to explain how exactly they're getting this one. There is another way that you see that, not just this way. We're going to explain it. Now, we said that we're going to take this triangle here. This is A. this is a, and this will be 4r, so a squared plus a squared is going to give us 4r squared. Now, opening up this one, it's very easy. It's very easy to do this calculation, but let's just do it to see that you may have something different. You may not get this one. You may not get this one. Let's say y. So there will be 2a squared is equal to 4r squared. I mean, the easiest way that they will say what? So okay, you can take root for both sides, yes? You can take root of both sides, or open it up, might be easier. Let's go for the opening up. A squared, to see what will I get? 2a squared. On the other side, if I open it, will be what? Will be 16r squared, yes? And then these two will come under here. What will happen? We'll have a squared will be 8r squared. Now take the root. What will happen? This will be a. The other side will be root 8 and root r squared. So we know that the square is going to go with the root. It's going to be a is equal to root 8r. This is the relation we have it. Now we know in mathematics root 8 can be rewritten in this manner. 4 times 2, yes. This is why it comes in this way. 4 times 2. And we know that it can be root 4 times root 2, and root 4 we know that it's 2. That's why we can rewrite it in this manner. 8 can be written 4 root 2. That is written here. Sorry, 2 root 2, because root 4 will be 2 root 2. This is going to be 2. So instead of root 8r, you can write it 2 root 2r. 2 root 2r. This is the way that we find the relation between a and r. There are other ways. I can do it in a different manner. Let's say from here, what do? I will take root for both sides. 2a2 is equal to root of 4r squared. What will happen here? The root gonna go with this square. For this one we have to divide it into 2, yes? For root 2 and root a squared. Let me just do it somewhere nice. Sorry. The first one is easy. Let's say for the second one. In the second one, we're gonna do it from the beginning. So it will be 2a squared equal to 4r squared. Now what will happen if I take root for both sides? We're gonna write this one root 2. I need you to know this one as well, because in some books they represent this way. Root 2. We're gonna do step by step. The root is gonna take this square. This already here it's easy. This is gonna go with this one. It's gonna go with this one. Here remain 4r. If I rewrite it, what do I get? I'll get root 2a is equal to 4r. Now if I write a is equal to 4r over root 2. This is also possible. Some book they represent in this one. A is equal to 4r over root 2, or isn't the same. By the way, it's going to be the same. it's going to be the same thing. Divide 4 over root 2, divide 4 over root 2 will be exactly by 2 times root 2 will give you the same answer. Will give you the same answer. I mean, mathematically saying that 2 root 2, let me just write it for you, at least to know what I mean. 2 root 2 is equal to 4 over root 2. Mathematically, they are equal. I mean, if you multiply this by root 2, divide, it's going to be the same answer. That's why whether you're using a as 4r over root 2 or you're using a is equal to 2 root 2r, is still the same. So whether you're finding in the third method or this one, you're still having the same result. Yeah, it will be different. A is equal to something. Say, sir, why is in some book is 2 root 2r, in some of them they're using 4r over root 2. You're supposed to know both of them are the same. Are they equal? They are equal, mathematically equal, so it doesn't matter which one you're going to use it. Mathematically equal. We'll come back to the volume later, the volume of a cube. We know that it's a cube, so if you have a, you can find the volume of this cube. This is how we find the relation between the lattice parameter a, and the radius of the atom in the face-centered cube. Now the coordination number here, it's 12. Let's say if you're taking one atom, it's basically linked, or the neighborings will be 12 atoms there. The links that we have them here, this we call them a coordination number. In chemistry, that will be useful to understand the coordination number for the purpose of bonding. There we have it. There's a coordination number, we have 12 atoms. We calculate number of atoms per unit cell. As we said that we have, for the face atoms shared by 2 cells, written here, face atoms shared by 2 cells, corner atoms shared by 8 cells. So that's why 8 corners, 1 over 8, 6 faces, 1 over 2, and the total number of atoms inside that unit cell, we have 4 atoms inside the unit cell. We'll come back to atomic packing factor with a separate video. So this is, we call it face-centered cubic crystal structure. You have to understand it, and we're going to use this one later for a lot of calculation. Thanks for watching.